Okay, so we want to talk about inverse functions a little bit, and what is an inverse function? Oops, I want to go over to this other graph. So what an inverse function does is it takes x and y and it just flips them. Okay, wherever you have an x, you have a y, wherever you have a y, you have an x. So here's our good old favorite function, y equals x squared. I'm going to change the color on that and just make it red. And so if we switch x and y on this, what do we get? Well, we'll just place my y with an x, that gives me x, and my x with a y squared. So the red graph is y equals x squared. The black graph is y squared equals x. And what we did is we just flipped the x's and the y's. So what does that do to points on the graph? So if we think about points on the red graph, 2, 4, for example, 2 squared equals 4, that gives me this point. If I switch the x and the y, that gives me the point 4, 2. That gives me a point on the black graph. If I pick the point, say 3, 9, that gives me that point C up there, 3, 9 on the red graph. If I switch the x and the y, I get a point on the black graph. So that's D. If I pick a point on the black graph, say the point 4, 1, oops, sorry, 4, -2, I don't know why I said 1. That's down here, and then if I switch the x and the y, that gives me a point on the red graph. So every point on the red graph corresponds to a point on the black graph. We get those by switching the x and y coordinates. There's 2 points that are on both graphs, 0, 0, for example. If you try and switch the x and the y, you just get the same point back. Same thing with 1, 1. So those are 2 points on the same graph. So there's a certain relationship between this, and Geogebra is actually quite nice for this. We can take, construct a line segment. Let's see, what's my constructing line segments? I should know. Oh, it's down here. Okay. I can connect C and D. I can connect A and B. We got those by reflecting things. And we can connect F and E, for example. That actually goes through the point 1, 1. So all of these points have midpoints. I can construct the midpoint just by clicking on that. Click on midpoint or center. It's there. Midpoint of this is there. So where do all of those points lie, all of those midpoints? Well, if we graph the line y equals x, that goes right through it. So we'll change the color on that to some kind of blue so that we can see it. So the red graph is y equals x squared. The black graph is x equals y squared, switching the x and the y's. There are corresponding points on each graph, and the midpoint of the line segment connecting the corresponding points lies on the line y equals x. So when we switch the x and the y's, what do we do to the graph of the red function? Well, we're just going to flip it over the line y equals x, and that gives me this function. So this point C, you flip it around the line y equals x, gives you the point D. This point A gives you the point B. And in general, if you pick any point on the red axis, you get a point on any point on the red graph, you get a point on the black graph. That's sort of a reflection in the line y equals x. So one thing to note here is that the black curve is not a function. It doesn't pass the vertical line test, right? The red curve is a function. It passes the vertical line test, but the black curve is not. So let's look at a different function. Here's a function. This is given by this formula here. So if we switch the x and the y in this formula, what do we get? Well, we can actually graph that pretty quickly without having to do any kind of complicated calculations, because if we put on our line y equals x, right, and we'll make that blue again, color blue, so there's the line y equals x. What we can do is we can flip this green line over that line y equals x, because Geogebra has this thing, reflect about line, right? So you click on something, you click on the curve you want to flip, and you flip over the line you want it to flip over, and you get that. So if I switch all the x's and y's on this green curve, I get this green curve. So that's nice, right? And you can get, you know, -3, -2 is this point. So there should be a point x equals -2, y equals -3. So these 2 points tie into each other. So this green curve reflected over the line y equals x gives me this green curve. Unfortunately, the second green curve is not a function. And why, and how can we tell if something is a function? Well, let's put in the line y equals 1, right? And that's a nice horizontal line. It's this black line. What do we get when we reflect this black line over the line y equals x? Well, 0, 1 is going to come down here. This point, -1, 1 will come down here. In fact, if we flip a horizontal line over the line y equals x, we'll go down to my transform. I want to flip this line over that line. I get a vertical line. And this vertical line tells me that this green graph is not a function, because it's a vertical line that goes through the green graph in 3 different parts, one here, one here, and one here. So this green graph not being a function happens because this green graph does not pass a horizontal line test, right? This horizontal line goes through this graph in 3 different places. That means when I reflect this green line and this black line over the line y equals x, I'll get a vertical line that goes through this green curve in 3 different places. And so this green curve fails to be a function. So this curve fails a horizontal line test. So its reflection in the line y equals x is not a function. On the other hand, if we take a function like this, and we look at the line y equals x, there that is, and we'll make this blue again, so that I keep my color scheme. We can reflect this green curve over the blue line. So reflect about line, this green curve over this blue line, and that gives me that green curve. And this second green curve here, this is the graph of a function. Every vertical line goes through it in exactly one spot. So if I start with a function that passes a horizontal line test, which means that every horizontal line goes through it in exactly one point, then the inverse function, which is what I get when I switch the x's and y's, or when I reflect it over the y equals x line, is actually a function. Its graph passes the vertical line test. This is important when we're dealing with exponential functions. So here's the graph of e to the x. E is just a number again. It's about 2.7. So there's the graph of e to the x. It passes a horizontal line test, so it should have an inverse function. How do we check that? Well, we'll put in the line y equals x. And for some reason, it's making all my lines black. So we'll make it actually blue again. So there's the line of y equals x. And if I flip that over if I flip the graph of y equals e to the x over that blue line, I get this green line. And that's a graph of a function. And it shares some characteristics with this green line, right? So that's the graph of e to the x. E to the x has got a nice horizontal asymptote over here to the left. This function has a vertical asymptote down here, never actually touching the y-axis. It gets closer and closer to it. E to the x goes through the point 1, 0. Oops. E to the x goes through the point 0, 1. right? And its reflection, if you switch the x and the y's, goes through the point 1, 0. This function has another name. In Geogebra, if you type in log and then e comma x and graph it, oop, no 0 there, and graph it, notice that this red graph, that's this formula, overlies the green graph that had been there before. So the logarithm is the inverse function of the exponential, and vice versa. The exponential is the inverse function of the logarithm. They're symmetric about the line y equals x. Exponentials go through the point 0, 1. Logarithms go through the point 1, 0. And they're inverse functions, right? They're just switching the x's and the y's, really. Okay.